Swayam Prabha. Digital India. Educated India.
So welcome to this 10th lecture in the Skian course on what are we doing? In the Skian course in high fidelity lattice Boltzmann methods. And now we come actually to the next central part, or the more practical, namely the cumulant methods that will now deal with all the problems that we have discussed yesterday, and also will deal with some of the problems that you may have encountered during your own programming yesterday with these long equations. Some of them. For a few others, you have to wait till Friday. Okay, we are coming to the good stuff now. First, let us remind us what have been the problems with this MRT methods. We have seen that actually by this orthogonalization we wanted to get rid of the dependency between the moments. However, this was not possible. We still have here a dependence of moments onto each other. So this could be overcome by some special weighted orthogonality which felt a little bit ad hoc. And remember, we could overcome a special problem there, but it was not clear whether with other moments we would have a similar problem, right? So we specifically, we saw one problem, yeah? You see one crack and you fix the crack. You don't know whether something else is wrong. So this was not something that looks very sustainable, actually. And it was not so clear how we get these things in a general way. So how do we get the weights? Where do we get the weights from? Then there is another problem that we've not discussed in this detail, but that was a little bit the subject of yesterday's hackathon, namely that the moments, they are defined in an Eulerian frame. So all the moments are defined in a lab frame, and now the question, of course, is what does this mean for the Galilean invariance of the model? Yeah, I mean, we define a specific resting frame and do all the calculations in the specific resting frame. So does this actually make, is this physical? So, you know, from physics, all the differential, everything in the world should behave independently of the inertia frame of reference. Yeah? So it may depend on the acceleration of your frame of reference, but not on the actual velocity of your frame of reference. This is what we have been told. So the question of Galilean invariance arises here. So the first thing you could do in order to overcome this problem with the Galilean invariance is what you did yesterday in the hackathon. You can use central moments instead of raw moments. in your MRT. Say central moment MRT. So taking the moments in the Lagrangian, the material frame. So as a reminder, but now you all should be very familiar with this, we have the Ra moments. So they are Eulerian. And we call them M, A, B, C, and they are the sum over the indices I, J, and K. I by the power of A, J by the power of B, K by the power of C, into F, I, J, K, and the central moments, which are Lagrangian, we call them K. A, B, C equals to the sum over I, J, and K, I minus U by A, J minus V by B, and K minus W by C, F, I, J, K. So, and here, of course, we know that the central moments are defined such that the first central moment is always zero. So this is the velocities U, V, and W are defined that these moments are zero. Okay, now what you did yesterday, and what was, of course, the expected solution is you'll take this definition, yeah, compute all the moments from the populations, and then invert this system and get long equations that give you they give you the moments given the populations that you later need for streaming. So there is a way this can be done in a different way. So, I mean, it's not really different, but you have recognized that it is easier to do this transformation with Ra moments. And then there's also a possibility to do a transformation between Ra moments and central moments. And this may or may not be of advantage here. So what you can do in order to make your equations look a little bit simpler is you apply a binomial transformation, and you first calculate the Ra moments, and then you can calculate the central moments from the Ra moments, and vice versa. So you can do a transformation between different frames of reference. So for example, so this does not, by the way, so this is a transformation from one frame of reference to another frame of reference. It is not required that one of them is central. Yeah, they are just two different. Yeah, but we are now assuming that we calculate the central moments from the Ra moments, and this is done through these sums here. So we sum alpha from 0 to A, we sum beta from 0 to B, and we sum gamma from 0 to C, and then we have this binomial A over alpha, B over beta, and C over gamma into -1 by the power of A minus alpha plus B minus beta plus C minus gamma. It's a little long here. Then comes the moments M alpha beta gamma, M so here comes the velocity actually, the zero moment divided by, the first moment divided by the zero moment, alpha by the power of, no, that's not, a minus alpha times, I mean, you can imagine 0, 1, 0 divided by m0, 0, 0 by the power of b minus beta, and this again multiplied by m 0, 0, 1 divided by m 0, 0, 0 by the power of c minus gamma. Okay, this equation itself is a bit tedious. I always have to remind myself about the definition of the binomial, also how it's written. So a over alpha is defined as a factorial divided by alpha factorial times a minus alpha factorial. Yeah, so this is this permutation here. So, for example, in 2D, this means that k to 0 can be written as m to 0 minus m 1, 2 divided by m 0, 0. And this can be written as m to 0 minus u square rho square divided by rho is also can still be written as m to 0 minus u square rho. K11, for example, is m11 minus u v rho. Okay, if you look at this equation up here, so one thing that you may notice is that the KABC only depends on moments of lower order than itself, and by the way, only in a linear fashion. So linear, not in the sense, so linear in these moments other than the first moments. So there's never a product of a second moment and a third moment in it. So only these higher order moments together with the lower order, with first order moments. Actually, this is a shortcoming of the central moments, and we'll see later with cumulants that this is different there. So, but anyway, you can here do this transformation, and equally you have the transformation of the equilibria. For example, m20 is u square plus theta times rho. This is equivalent to saying that K20 equilibrium is equal to theta times rho, and M11 equilibrium being u v rho is equivalent to saying that K, so this is supposed to be 1, sorry for my bad handwriting, equilibrium is 0. Okay, so this is what you've already determined yesterday. Because when we are in central moments, then the equilibrium of these central moments is not a function of the velocity. So velocity, in central moments, velocity comes up in the transformation, forward and backward, but it is no longer in the equilibrium. So, question, does this help us with Galilean invariance? are saying that we have not yet verified that actually we have a problem with Galilean invariance in MRT in the first place, so let's have a look. So Galilean invariance, what does it mean? The frame of reference. Okay, I should be more precise. The inertia. The inertia frame. So it is, of course, if you have an accelerated frame of reference, then there is a Coriolis force, a centrifugal force, these things. Yeah, but otherwise, the inertia frame of reference must not influence the behavior of the system. So let's have a look first at raw moments. We relax raw moments and see what this means for central moments. And we start with the second moment. These are the ones that we are actually interested in the most, right? Because they appear in the Navier-Stokes equation. So we have m20 after collision is m20 plus omega 20 m20 equilibrium minus m20. Okay, so this is what we do, what we may do in MRT. Of course, to be more precise, in MRT, we will split this thing up, yeah. But let's assume this we would not split it up into its isotropic and non-isotropic part. Now let us replace all these moments with their central moment counterpart. So this is K20 star comes with U square rho. So I'm just replacing this moment here with its central moment counterpart. Next, I will replace this moment here with the central moment counterpart. So this is now before collision K20 plus U square rho plus now comes omega. So this is still the collision done in raw moments, not central moments. Yeah, I'm just replacing the variables. The equilibrium, okay, the equilibrium is K20 equilibrium plus U square rho minus K20 before collision minus U square rho. So now what do we observe? We can eliminate these against these and these against these and get K20 after collision is K20 plus omega 20 K20 equilibrium minus K20. Is this good or bad? Who is for good? Who is for bad? Who doesn't know? You know, it made, according to the Bible, it made the humans human because they could distinguish good from bad, good from evil. Okay, I didn't say evil, yes. So this was now very, very stupid European style. So, I mean, look at it. If we had the if we implement the things in central moments, this is exactly what we would do, right? So this is actually exactly what we expect. It looks exactly the same as if we did it with central moments as with non-central moments. And this is, of course, the reason why MRT works. So we know that we need to be accurate up to the second moment, otherwise we don't get to the Navier-Stokes equation. Yeah? So if there was a problem with Galilean invariance here, then we would have discovered this long ago. Okay, so no problems with the Galilean invariance here. So this guy is frame independent. Frame independent, so this applies, by the way, to all second order moments, K20, K02, and K11. By the way, this is only true if there is no force. Yeah? So if you have a force, then this may be violated. And this is the reason why there are so many ways in Lattice-Boltzmann to compute forces. Yeah? Because you want to avoid that this you want to avoid this violation here. So, but assume there is no force. Do you have a question? Please take the microphone. Is it on? So the question was about gravity.
Question was about gravity. So if you want to include gravity,
yeah, then you have a force.
Yeah. So then
yes, then you have then you have to reevaluate.
Okay.
I mean, this then depends on how you implement your force. Yeah. So there are ways that would cause a Galilean problem here, and then there are better ways that do not cause Galilean problems here. Yeah. So this is why there are many different ways of calculating the force in Lattice-Boltzmann. So, okay, actually, it is not surprising that to second moment it works, but there are also the higher moments which are not directly influencing the leading order, so the solution that we get, but they will influence the error. And the error is something that we accept as there, but we always want to have it as small as possible. So let's look at the next order, and specifically the third order moments. So say we are still in 2 dimensions, and we look at our binomial transform, saying us that K21 is equal to M21 minus 2U M11 minus VM20 plus 2U square V rho. So now there is something, so there's now a difference between this moment and the other. So here, what we have seen, if there's no force in the second moment, then the modification between, so the difference between the central and the Ra moment was this, and this thing was Galilean, was collision invariant, because at least as long as there is no force. Yeah. So this would stay the same before and after collision. Now there is a difference here, because here we have something that is not invariant under collision. So we call it collision variance. Collision variance. And only this here is collision invariant, as long as there is no force. So now we have to, because we want to express this moment here completely in terms of central moments, we also have to replace this and this, right? So let us remind, we have M11 is K11 plus UV rho, and we have M20 is equal to K20 plus U square rho. Meaning that we can now solve this for M21 and get K21 K21 plus 2U K11 plus V K20 plus U square V rho. Okay? So now this is the M21 expressed completely in central moments and velocity. And what we are now going to do is we look at the relaxation in the Euler frame. This means the relaxation of Ra countable moments. Euler frame. So this would now look like this. We would have M21 after collision. Yeah, so we assume no orthogonalization here at this time. M21 after collision is M21 before collision plus omega 21 M21 equilibrium minus M21. So this is what happens in a non-orthogonalized MRT method. Now we replace everything by central moments. So the left-hand side, K21 after collision, is then 2U. And here comes K11. And this, of course, because the entire thing is after collision, this is also after collision, right? Plus V, K20, this is also after collision, plus U square V rho is equal to, now comes this here, which is before collision, K21 plus 2U K11, and this is now before collision, and now you already notice that previously these things would cancel out, but they no longer cancel out. Yeah, K11 plus V K21 plus U square V and rho, and then comes this part here, K omega 1, 2. So now what comes here? We get K12 equilibrium plus 2U K11 equilibrium plus V K20 equilibrium plus U square V rho, and then the pre-collision state again, K21 minus 2U K11 minus V K20 minus U square V rho. So okay, so this part you can get rid of, right? It's also on the other side. See, okay, no, this was the wrong. So I can cancel this against this, and I can cancel this against this. Yeah. So and this is now almost everything that I can cancel. Now I have to decide what these things are. These post-collision states. Now these post-collision states, they are actually obtained through the collision operator. So we have seen this, that they are Galilean invariant. So I can just write them down. K20 equilibrium minus K20. K11 is K11 plus omega 1, 1 to K11 equilibrium minus K11. So now we introduce this here, having K11 after collision plus okay, my notes have mistake, I guess, so I'll try to okay, I'm already doing a simplification here, because we see that this K20 star asterisk always comes with the pre-collision state first. On the other side, we have the pre-collision state. Yeah. So I already eliminate this here against that here. Yeah. In order not to write too much now. Yeah, but what is always left is then this the second part, this u. Let me see. This is 1 1. Yes. So this k 1 1 equilibrium minus k 1 1 before the collision. So this is left plus v omega 2 0 k 2 0 equilibrium minus k 2 0. Now I've eliminated all these. I've eliminated all of these on the other side already, so I'm no longer writing them down. And coming to k1 2 plus omega 2 1. Here comes k2 1 equilibrium minus. Okay, I'm grouping. What I'm going to do is I'm grouping this with this here. It's k2 1 plus 2u, and I'm grouping this here with that here. So it's k1 1 equilibrium minus k1 1, and then I'm grouping that here, this here with this here, gives me plus v k2 0 equilibrium minus k2 0. Hopefully this is correct, and this is what we have. And now we can rewrite this a little bit more in order to see that this gets to k1 0 after collision is k1 0 plus omega 2 0 k2. Why do I say it? Why can't I just say what I'm writing? Omega 1 2. So usually my writing is better than my speaking. Yeah. So it's, but you've learned this already, I guess. Yeah. Oh, I see so many smiles here. Okay, k2 1 k2 1 equilibrium minus k2 1. So okay, see, this is what we would expect, right? So this would be the Lagrange frame. If we did it in the Lagrange frame, we would get this. However, there's something left, and the thing that is left is u omega 2 1 minus omega 1 1. So u. Okay, I have another mistake in my k1. Let me see whether this is. Okay, k1 1 equilibrium minus k1 1 plus v omega 2 1 minus omega 2 0 times, unfortunately this doesn't fit here, k2 0 equilibrium, let me give more space, k2 0 equilibrium minus k2 0. So this here, all of this is in violation of Galilean invariance. Now I just need to be able to write. So why is this in violation of Galilean invariance? Why is it important that there is a velocity in it? I mean, it's not important whether there's a velocity in it or not, because here could be a velocity in. And the thing that violates Galilean invariance is that there is this, if k1 1 is out of equilibrium, yeah, then this generates or destroys some moment k to 0 at k to 1 if and only if there is a velocity. Yeah? So the decay of this moment depends on the velocity, which is, of course, not physical. So, okay, now we have discovered that lattice-Boltzmann is not Galilean invariant, and I know that there would be some old guys standing up in the audience and say, well, it cannot be Galilean invariant because it is a discretization on the lattice. Yeah, so we have finite many speeds, and this obviously makes it non-Galilean invariant, which is absolutely true. However, the violation of Galilean invariance that we have here is worse than the one that comes from the discretization. And one way of seeing this is that we have not used the discretization. We were just talking about the moments. Yeah? Nowhere did we assume any discretization. So even if we had a perfect discretization, we still had this problem. Another thing that we can discover is that the BGK does not have this problem. Why am I saying this? Why does the BGK doesn't have this problem? Anybody sees this? Please. Because they have the same omega. See, you see this here. If the third moment and the second moment all have the same relaxation rates, then this here disappears, and so there's no violation. Yeah? So BGK does not violate Galilean invariance in that way. Of course, due to discretization, it may violate Galilean invariance. So let us take this to note. So the third order moments, they are not Galilean invariant. In the classical MRT. BGK, as you noticed, omega to 1 equals to omega to 0 equals to omega 1, 1, means BGK is Galilean invariant. And the other thing of note here is that the violation of Galilean invariance is not due to the discretization. As we see from the fact that we did not assume any discretization so far. None assumed in the analysis. So, now we have this multiple, please take the mic.
So in the previous page,
Yeah, previous page.
Little before.
The page before.
Yeah, so there. No.
Here. Where?
Yeah, so yeah, when we are starting K21 star, so we are writing that after the collision.
Yes.
So here U is still, U is not U star because we don't have any forces.
Okay, yes. Okay, so right. So I was not assuming that there are any forces, so that there would be U before and after collision would be the same. Yeah, I don't want to complicate this any further. This is complicated enough. If, as I said before, so if there is a force, you have to take the manipulation of the force in the second orders into account in order to get the correct stress. Yeah, there are several ways of doing this. So you have these GU forces and so on. They all have a correction in the second moments. And then there's other ways of doing this, applying half the force before and applying half the force after. So adding a specific forcing step to the method will also enable this. Now we have seen that there are at least two problems with the MRT. The one problem is that these moments are not independent of each other. Yeah. So, and even if we take them orthogonal to each other, then still they are not independent. So this is a big problem. And the other problem is by relaxing different moments with different rates, we lose Galilean invariance. All of this together may lead us to the question whether moments are actually the right way to go forward. And well, yeah, I mean, of course, I wouldn't ask this question if I wouldn't have an opinion about this. But I can assure you that still many people in this field assume that moments are still the best choice, and yeah, but moments can be different things. So here we want to propose something that, in my opinion, is the better choice, namely cumulants. And now we have to introduce what cumulants are. So cumulants is something that looks pretty abstract from the outside, and once you got them, they become strangely natural in the inside, if you will. Anybody anywhere familiar, I mean, out of letters Boltzmann, what cumulants are? Okay, let's try to learn something here. Yeah, they have lots of applications outside of letters Boltzmann, by the way. Yeah, it's a very interesting topic. So first of all, so we want variables to be independent of each other, and for this we first have to try to understand what we actually mean by being independent. So variables now I wanted to say something. I wanted to say something else before. If variables are not independent of each other, so meaning there's a correlation between these variables. Yeah. So, I mean, your child is growing, and at the same time it becomes heavier, say, right? So it gets longer and heavier. And these two things are somehow related to each other, right? So it would potentially get at the same, so it would be surprising that if it gets taller, your child, on a different time scale, then it becomes heavier. I mean, maybe, or is it, this is maybe this is not the best example. So take the water bottle, yeah. So in this water dispenser, yeah, and it would be surprising that if the water line gets high, it would increase on a different time scale than the weight of the water bottle, yeah. That would be surprising. So because these two variables are connected to each other. So now what we propose is that we want to see an evolution of different variables on different time scales. And now when these variables are physically coupled, that one follows the other, then it is physically not feasible that they have different time scales, obviously. Yeah? They would always have to come together. So, and Therefore, their relaxation rates have to be coupled, but this is not what we want. We want to decouple relaxation rates. So, I mean, if two variables like the water line and the mass in the water bottle are somehow completely coupled, then this actually would make sense. So coming back to the child that is growing while getting in size, but is growing while getting more mass. So this is a little bit more complicated problem, right? So people get more mass even if they stopped growing. So there is, of course, there's a correlation between, your weight and your height, but there's also something that is uncoupled. And the idea is now to separate these variables, that you look at things that are really genuinely working on different time scales. But for this, now we need to understand what it actually means to be independent. So what are independent? Random variables. And I remind you that we are talking here about random variables because we are all the time talking about the probability of a finding of a particle in a certain state. So it's always a random variable, yeah? So we only talk about the probability finding particle. So when are random variables independent of each other? Can anybody give me a guess what this means? So, what independent variables do we have in the first place? We pick a particle, yeah? And so I pick this particle here. Okay, I'm not holding it, otherwise I would change the velocity, yeah? But say I select a particle, and this particle has a velocity in x direction. And it also has a velocity in y direction. So if these two things are independent of each other, then having the knowledge of its x velocity should not give me any knowledge on its y velocity. Yeah? This is what we mean by independence. So statistically, if I know something about one variable, I shall not know anything about the other variable. Whereas when they are coupled in some sense, so for example, you throw three dices, say, and you know the combined number is, say, 9, because somebody told you, and then you also know that one of the dice shows the number 2. Yeah? So you still don't know what the other two are because they are different combinations, but you know something about it. Yeah? You have reduced the probability. Yeah? So, but they are still dependent on each other. So an independent means you know nothing. So, yes, let us write this down. Knowledge of, say, the state of, say, one variable is x. So if we have knowledge on this implies no knowledge on the state of y. So let us, to see how we get there, let us recall the moment generating function. the moment generating function in its original definition. So this was the bidirectional Laplace transform. You can also write it as a Fourier transform. Yeah, then you need some complex variables. Yeah, I mean, but this is the same thing here. So we integrate over all the velocities e by the power of the velocity without minus. So it's actually the inverse Laplace transform if you are more accurate mathematically, but whatever. So and say this function f is also a function of all its moments, obviously. Yeah. Anything confusing? Yeah, so this is a Laplace transform. Actually, the original Laplace transform has a minus here. We have the opposite sign convention. This is like you're doing an inverse Laplace transform. Is it? Yeah, we changed the sign of the exponential. Yes. And the other thing is we have a bidirectional, yeah. So it goes from minus infinity to infinity. My computer seems to have a problem here. Still everything running? I hope so. So this is actually our probability distribution in this frequency space. So frequency means the velocity frequency capital Xi instead of the small xi. So now the thing with independent variables is that there is the factorization of their distribution. So you are certainly aware that if there are independent events, yeah, coming together, so this is very important because events are very, very often not independent. Very, very, very often not independent, yeah. But if the probability that, you know, if the probability that there is a rain in Chennai in March is, I don't know, 1 in 100, and that I see a tortoise on the Madras Avenue is 1 in 100, then the probability that the combined probability would be 1 in 10,000, unless of course the probability of these two things are somehow combined, right? So, which they would be, because the tortoise comes out when it's raining. So, but if they are really independent, we get this factorization of probabilities. Now, and this is something that we want to use now, because the factorization of the probabilities also applies to their distributions. The distribution functions also factorize. So we can write this f, which is a function of the moments it is made out of, and the moments are not necessarily independent of each other. So it does not factor, so this distribution does not factor in terms of the moments, but we now propose that there are variables for which this is independent. So this is important. We just assume there exists independent variables. Yeah? And if there exist independent variables, then this distribution would factorize, so we can write this as a product in these independent things, where we have independent distributions fi, of which each depends only on one, of which each is a distribution for only one of these variables, ci. So now we think we can write this as a product. Okay, let's also write this down for future reference. So if ci and cj are independent, their joint probability, so this is the joint the joint probability is the probability that both of them come together. Into their individual probabilities, individual probability distributions. Okay, this is a nice assumption, but now we have not yet identified how these variables would look like. We just said that if variables like this exist, then they would have this property, right? So let us come back to our moments in our moment generating function, and I remind you that the velocity frequency was defined as the vector of xi. So this is supposed to be an upsilon. I never write this properly, and zeta. So these are the three different velocity frequencies. And I remind you that the moments were defined like this, M, A, B, C, as these derivatives, the 8 derivative in xi, the B derivative in upsilon, and the C derivative in zeta of the moment generating function, and all of this evaluated at frequency equal to 0. So now, as I told you when we introduced this, these are the coefficients of a series expansion of this moment generating function. You know, when you take a Taylor expansion of something, you need the derivatives at a development point, and the development point is here 0. So actually, you can write this in inverse, saying that we recover the moment generating function as a series, so going over all the moments A, B, C from 0 to infinity, with xi by the power of A, upsilon by the power of B, and zeta by the power of z, divided by A factorial, B factorial, C factorial into M, A, B, C. And now, if you replace this M, A, B, C by these derivatives, and you are hopefully familiar with the Taylor expansion, you see that this is exactly the three-dimensional Taylor expansion. Yeah? So this is exactly the three-dimensional Taylor expansion of this. which when you go to infinity and it is converging, then you actually get the right function, right? So what we observe here is that we can write this the moment generating function as a sum of the moments, yeah, with the appropriate prefactor. So now, how would this work for independent variables? Let's have a look. So for independent variables, so all we know about our independent variables is that the probability distribution factor, so that we can write this as I equal to 0 to infinity over fi ci. So the product. Now here we have a product, here we have a sum. Yeah? So this is not compatible. What we would like to have is here a sum too. So how do we get a product to a sum? Any idea? Logarithm, right. We'll take now the logarithm of the moment generating function. So when we take the logarithm of a moment generating function, then we have here the sum of the individual distribution functions that all depend just on one independent variable. Yeah. So we've not designed what the independent variables are, but we see that they have to behave like this. Yeah. And now you can see that if you take now the Taylor expansion of the logarithm instead of the function itself, the coefficients thereof are now by design independent variables, right? So meaning that we now define the cumulant generating function as the logarithm of the moment generating function, and we simply say that they behave the same way. So we have a sum over a, b, c coming from 0 to infinity, and we sum this over xi by a, epsilon by b, and zeta by c, right, by a factorial, b factorial, c factorial, c, a, b, c. So, and this can equally be written as CBC as the derivatives xi and epsilon and zeta of now the logarithm of the moment generating function evaluated at frequency 0. So now these are cumulants. And we have designed them in such a way that they are independent of each other. So everything that we now wanting to do is just to use MRT with cumulants instead of with moments. So what we hope to achieve by this, that we have independent variables, and we also assume that we have Galilean invariance in as much as the discretization allows us to have Galilean invariance. So, now first thing with cumulants is so when we had this idea using cumulants, so I have to admit between the idea of using cumulants and actually being able to publish a paper on working cumulants, there were 8 years. Yeah, because the thing has there's a lot of detail that you have to care about. And the first thing is, if you now go to a book, and I remember I had I had a book by a man called Gardinger on cumulants, and the first thing what was written there is no easy way to compute cumulants. Yeah, I mean you see here this definition, but this definition does not give you a good idea how you would actually now calculate these things. It looks like that you have to use a Laplace transform, and then when you have the Laplace transform, you have to take the logarithm, and then you have to do all these things. So this doesn't look very intuitive what you should do now. Yeah, actually, it is not so bad as long as you don't try to calculate them directly. So how do you compute cumulants? Let's look at the cumulant C001. So this is obviously the first derivative in zeta on the logarithm of f, and this evaluated at xi equal to 0. So now instead of doing all the calculations here, is what you do is you are just applying the chain rule of differentiation to see what this actually means, and you see you have to take a derivative of the logarithm. So you have an external derivative. What's it called? Yeah. So you have to differentiate the logarithm. The logarithm gives you 1 over f, yeah, and then you have an times the internal one, that is 1 over f by f, and now you have to apply this equal to 0. Now, how would you do this now? Actually, from here on, what you can do is you use the definition of the moments, because you know that the first derivative in zeta of f is at xi equal to 0, yeah, is m001, right? But then you have 1 over f. What is this? 1 over f at xi. So what is f? F xi at xi equal to 0 is the 0 order moment, right? So it's rho, right? So it's m000, right? So so this comes out as m001 divided by m000, and this is the velocity. So compared to the moments that we had previously, moments, because we did not normalize them, moments are extensive quantities. That's the momentum. Here we see intensive quantities. Yeah? We see something that, I mean, after all this abstract stuff, we can actually understand very well. That's the velocity. The velocity comes out as a cumulant. So, looking at something else, C002 is the second derivative of the logarithm of f, again at xi equal to 0. Now, what we are going to do simply is we're taking this thing up here and take another derivative of that. So we'll have to take a derivative of 1 over f. Yeah. So there's again an internal, and an external. So the external gives you f by the power of minus 2, and the internal gives you d z f again square. So it gives you dzf times dzf, yeah? It gives you dzf square, and then you have to apply the product rule. So you have applied. So first we applied the differentiation to 1 over f, and now we have to take 1 over f times the differentiation here, which is simply the second derivative, obviously, and here f remains. So now again, you see this here. dzf is now again the first moment. This here is the 0 moment twice, and dz to the second order df dx second derivative by theta. I need more sleep. This is obviously the second moment, right? So we get here minus. So this is obviously minus omega square plus m002 divided by m000. So, and if you do this for all the others, C002 plus C020 plus C200, what you end up with is actually 3 times theta, which is the temperature. So I always say, who was the first human being talking about cumulants? I believe there must be some Homo erectus woman who told her child not to touch the fire because it is hot. Yeah? I mean, it took us to the end of the 19th century that we could physically explain what temperature is. Yeah? But we always, all the time, we knew what it is. And now I tell you, the most compact way of saying what temperature is, it is the trace of the second order cumulants. Yeah? So we come with this very abstract mathematical concept, and what pops out is things that apparently we have known for ages. Yeah? The cumulant is the velocity, the next cumulant is the temperature. Very interesting. So, write this down. First, cumulant is velocity. First cumulant is velocity. The trace, so the trace is the sum of you know what a trace is. This is the sum of the the sum of the diagonal parts of the matrix. So there's a trace of the second order cumulants is the temperature. So as I said, if you don't take anything, if you can forget about letters Boltzmann, maybe you do something else in your life later, but maybe you come across cumulants and see that they are very useful things in many other aspects. Yeah, they also have applications in machine learning. So the idea is always separation of variables. Yeah, separation of information. So interesting is again that the equilibrium of all the naturally not conserved moments, cumulants, is 0. I mean, this makes absolutely sense because they should not depend on anything. Yeah? So they should be 0, otherwise they would depend on something. Here in Letters Boltzmann, of course, we do not conserve energy. So because we do not conserve energy, I could also write here now equilibrium. Yeah, should write this actually in a different color. Yeah, because we do not conserve equilibrium, we have to put temperature as an, we have to put an equilibrium temperature there. Yeah, as our equilibrium. So this may still look a little complicated. Let's look at cumulants as expressed in central moments. So we do a change of frame of reference according to the translational rules of the Laplace transformation. So the translational rule of the Laplace transformation is actually similar to what you have in the Fourier transformation. Are you familiar enough with the Fourier transform? What happens when you move the coordinate system in the Fourier transform? So say there's Euler, you have F, and you move this to Lagrange. So you have another F, and you have this comes with U times Xi. This is the shift in the Fourier transform. Have you, how well do you guys study Fourier transform? Not that much. So if in people who learn like electrical engineering, they usually do a lot of Fourier transform, I believe. So you're more mechanical engineers, I guess. Yeah. So Fourier, if you shift Fourier transform, then this is equivalent to multiplying this by this exponential function. Okay. If you're not familiar, and here we have to. It's not so difficult to prove this. So we have the sign convention is opposite to the usual standard. Therefore, we also have a u and not a u minus here. Okay, if you're not familiar, this is Ken. I guess you find this on Wikipedia. Yeah, if you look into calculation rules for Fourier transforms. So CABC. So again, this is defined. My ugly epsilon, zeta c. Now comes the logarithm of f times u xi into, so this evaluated at xi equals to 0. Now what you can obviously do is, because there is a logarithm, is you can put this into a sum and then you take the logarithm of the e function. We assume that the logarithm is a natural logarithm, does not matter, but we assume this. So this can be written as this upsilon b zeta c. So comes into u times xi plus the logarithm of the one that is now in the Lagrange frame. So because the f with the snake on top is in the Lagrange frame, so it does not depend on velocity anymore because it has been put into the centered frame, right? So there is no velocity in this function here. All of the velocity is here, right? So when you evaluate this, I mean, after evaluation of the derivatives, we put xi equal to 0. So say for the zero order moment, we put c equal to 0, then this is gone. Now, because this is linear in xi, only the first derivative will give us a non-zero value, and this will be exactly u, right? So this means that wherever we shift this, when we shift the f into the other frame of reference, we still get the same u here out. So this means because u only comes in the first derivative, and here is no u in it anymore, means that all but order 1 cumulants are frame independent. Meaning we get Galilean invariance by the fact that in whatever frame you are, you always get the same cumulants out. Yeah? So they are automatically independent of the frame of reference. Only the first cumulants depend on the frame of reference, and they give you the velocity in that particular frame of reference. Okay, next page. So, in practice, we prefer to write the cumulants in terms of central moments. You have a question? No. In terms of so because this is more efficient, then in terms of raw moments, we'll just see why this is the case. So let's look at this cumulant C002, which is M002 divided by M000 minus M001 and M000. Okay. Now we have seen that cumulants are the same in whatever frame of reference we write them, unless they are the first cumulant, yeah? So because they are the same in whatever frame of reference we write them, we can equally write them in K002 divided by K000 minus K001 squared divided by K000. Yeah? I mean, this is the consequence of them being the same in each frame of reference. Now, why is this simpler? This is simpler because usually if we compute cumulants, there will be in terms of moments, there will be many occurrences of first order moments coming here. And if we write them in central moments, then these first order moments are all 0. This is 0. Yeah? So it's very convenient, so it's more convenient to put this to 0 because K001 is equal to K01 is equal to K100 is equal to 0. Meaning that is K002 divided by K000. And this, of course, plays a much bigger role the higher the order of the moment of the cumulant is, because for higher order cumulants, the equation can and do get pretty long. Okay, last thing now is that we want to see whether the cumulants actually solve the problem that we had with the MRT. Yeah? So let's put the cumulants to the test. And here we recall the problem that we identified yesterday. With the M211 moment, you remember this is present in D3Q27. It's not present in D3Q19. This is why this method has been much more popular in the past, because it does not come with this problem. So we have seen, or actually I told you without really showing you, that we either get an overdamping or instability. So somehow wrong behavior in this method, or this cannot be avoided unless the moment is changed to n. So we make this change n211 equal to n m211 minus theta m011. So if we make this change, yeah, then suddenly this problem that the ghost moment would, increase in size was gone, right? So let's see how the cumulants behave in this way. Cumulants are, of course, more complicated, and this was also only one specific problem. But let's see. So how about the cumulant C211? So the cumulant C211 can be written as K211 divided by rho minus K200 times K011 plus K110 plus times K101, and this into 1 over rho square. So, by the way, you see one important difference between cumulants and central moments. If you remember what I said at the transformation of the central moments, I said that the central moments, if you write them in terms of Ra moments, they are always linear. So you never see they come with higher order moments times velocity, but they never come with a product of second order moments. Yeah? So now this here is a difference because what you see here is the products of all sorts of moments coming up. Yeah? So this is not the case when you transform Ra moments to central moments, but it comes up when you transform moments to cumulants. So now this is evidently more complicated than this, yeah. But let's see whether we can reduce it using the following facts, namely that we only had to look at this at a particular order. So the problem appeared at second order in diffusive scaling. Okay, coming back to our nomenclature from the asymptotic analysis. So with asymptotic, if we take the second order of C211, then we can write this as the second order of K1211 divided by rho to the zero order minus K200 to the second order times K011 to the zero order. And I remind you that there is no first order of a second moment. So because in principle, yeah, we have, okay, I'll write this down. So we also have first order K200, 011, first order, yeah? So you have, you remember when we have a product of two moments or anything else like this here, yeah, the order that comes up here must always be the sum of the orders here, yeah? Or the difference between this order and this order, right? So this must be 2 and 0 or 1 and 1. But you already know that these things do not exist, so we can eliminate them. Then there is K200 to zero order and K011 to second order plus 2K. Why is it 2K? It is 2K because I guess I've forgotten a 2 here. I've forgotten a 2 here. Sorry, yes. 2K11 to second order and K101 to zero order, of which we know does not exist, plus 2K11 zero order, K101 to second order, of which we know that this does not exist, plus 2K110 to first order times K101 to first order, of which we know that both do not exist, right, by rho 0 square. Now, this K110, as I just said, this is the same as K101 to zero order. So at zero order, they do not exist. But one thing that exists at zero order is K200. What is K20? What is K200 at zero order? Anybody remember? So K200 is usually rho times theta times u square. So u square is obviously of second order, so this doesn't exist. Then rho comes in order 0, right? So we have rho order 0, and then what is left is theta, right? So this obviously exists, and this K110 and the other one to first order, they are also 0. Second order moment, this is 0. Meaning that this cumulant becomes to second order C211 to second order is K211 to second order divided by rho 0, which is a constant, minus theta K011 to second order rho 0. Okay? And now you observe, actually this is, the entire thing is more complicated and it may capture more problems, but you see that this cumulant, up to the fact that it is normalized, behaves like this ad hoc correction that we did yesterday. So automatically, it will eliminate this dependency, that this spurious dependency that we had seen yesterday will automatically be eliminated by just using cumulants. So writing this down, cumulant removes MRT problem. And this means we are now actually finally free. Now we are free to choose. We have a free choice of relaxation rates for the different cumulants, which previously we had not. Okay. This concludes